So welcome to our postponed meeting. This is supposed to be last month, but due to lack of notice, not too many people showed up, so we postponed it to today. So it's a joint meeting with the Live Members Group and the Consultants Network. Of course, we are part of the Central Texas section. So our Texas Consultants Network, we promote the development of members' careers through professional and social networking, including publicizing members' skills and sharing potential professional opportunities. And we, of course, support the IEEE Central Texas section. We have a website, which you can also see from the newsletter that you receive every month for meeting news, and you can also get to the previous presentations and history and a bunch of other info. The Central Texas Live member Affinity group is actually a much larger group than the Consultants Network. We have probably over 400 members there. And membership here is kind of automatic. So I actually created a little formula here. You need to be just age 65 plus your years of IEEE membership to be equal to or greater than 100, and you automatically become a member. You don't have to do anything, pay anything, or do anything extra. So it's kind of good. I think a few of us on this list here are members. The Live Members Group hosts monthly meetings like this one with topics of general interest to generally more senior members. They are frequently technical, but also of general interest. And also there's a link in the newsletter that you can go to get more information. So we would like to ask for or request help for future meetings. You can suggest topics. You can consider to be a speaker yourself. Possible topics include technologies such as 5G, 6G, IoT, AI, and so forth, and or non-technical stuff like finance, hobbies, travel, and education. You can talk about your engineering story and your contribution, what you did or what you think it's nice and neat and useful. We also talk about health and aging, of course, and engineering and science history. And about once a year, we try to have a tour. It could be like this year, we have a tour to the Wildflower Center in South Austin, and sometimes they are tours, somewhat technical tours to engineering companies and so forth. All right, so this is the time for elections. So next year, obviously, we have all kinds of elections throughout the whole country of everything, but for our little IEEE groups over here, we do have annual elections also, which happens in November. So this is the slate of current members in our two groups, the Live Members Group and the Consultants Network. And we do ask and encourage volunteers to come participate and, just jump up and sign up. This is your society, your group. So you are all welcome to participate in any of these positions. So if anyone's interested, or if you know somebody that you want to nominate, just send email to Bill Martino for the live members, or to me, Luis Basto, lbasto@IEEE.org. So these are our email addresses. So we highly encourage people to do that. Future events. Next year, the Live Members Group will hold a conference, and this is actually not just local or even Texas. This is a worldwide Live member. So we expect hundreds of people, hopefully, to come to Austin on this date, April 14th to 16th. We will be at the Hyatt Regency Hotel. We are still working on it, and more information will be forthcoming. Everyone is invited, of course, and we are also asking for volunteers. For future topics, next month, actually, I'm sorry, this month, 2 weeks from now, we will have our normal monthly presentation on biotech and convergence technology by S. Collins. So you will see the newsletter coming out pretty soon after tonight. Next month, we have a networking lunch for the live members and consultants network people. So I think some of you, whoever is interested, should also let us know.
Is that my friend Scott Collins?
Yes, yes,
I think so, yes.
yes, Scott, yeah.
Yeah, we both mentor startups at ATI.
Oh, okay, great. So you might want to sign up for this meeting. I think the meeting, I don't know if they are open for sign up yet, but it should be open maybe.
It is.
Yeah, on vTools. Okay, so tonight's meeting, Kai, do you want to introduce Doug?
Yes. So Doug is the Chief Marketing Officer in Inspire Semiconductor. It's a new company in Austin for a few years. And he came out from IBM, was doing marketing there before, from engineering to marketing. Then he done a few company in the past, Cadence, Coldware, Newisys, and some in Austin, some are not, right? And also now he heads the Society of High Performance Computing Society. He's the president there, and his work is on RISC-V, International Special Interest Group, HPC. So he's a contributor to that organization. And also his volunteer work is working for Austin Technology Incubator. It's a UT program to mentor some small startups. And he got his PhD from Missouri, Science and Tech. Next page.
Next page is just kind of
okay. Maybe just kind of announce that. So we want people to be silent and and ask questions either by typing the chat room, or you do it after the meeting at the end of the presentation. So either way, it's up to Doug what we want to handle it. So Doug, you have the floor.
All right, thank you.
Louis, please unshare, and Doug share.
Okay, here we go.
Yeah. So I know what it's like to be out in the audience and have a burning question. And so if you have one that's just burning and I don't get to it within a minute or two, I'm happy to be interrupted. All right. So a little bit about our company and our team, I guess. So you heard a little bit about me. Those are just a handful of companies I've done after starting my career at IBM, and moving from the development lab. I meant to make full screen. Development lab into the field, and going through their kind of 2-year sales and marketing mini MBA program and all that. After a number of years doing that and evangelizing IBM technology and a lot of aerospace accounts and other things, and promoted to area staff and up and up and up, I just realized that I like building companies, not products. I became an engineer because I thought I wanted to build products, but I like building and scaling companies. So that's my thing. You'll see here from this leadership team, we're a very veteran team. That was very intentional. All of us have experience in both public and private companies. So we've been there, we know what it feels like to be big company success and scale, but we also know what it's like to be at a startup, kind of have that scar tissue, if you will, the lessons learned, being able to, not having a staff of 20, 30 people behind you, backing you up, having to roll your sleeves up and do it yourself. So on the left-hand side of the screen, our CEO, Ron, and CFO, John, and founder and CTO, Alex, they all met at SolarBridge. Ron and John have been, CEO, CFO team several times at various companies. Alex was the rock star engineer at SolarBridge with them. And that's, he wanted to start this company, and he did, with Ron as an advisor. And, pretty soon it was like, we need somebody on the finance side. then, 3 months later, I was brought on board as to, do business development and, validate what we were looking to build with my broad network of people around the world in HPC and AI, because I've been doing that for 35 years. Every time I try to get out of high performance computing and AI or expert systems or whatever we've called it over the last, 50, 60 years of AI, I always get pulled back into it, and it's just my peeps. It's what I do. So I've accepted it. Thomas, again, super experienced guy, started his career at Motorola, was doing a lot of the 68K, servicing customers, ramping up and all that. Then when the whole Apple, IBM, Motorola PowerPC thing came along, he was the guy driving that to supply the chips and everything. He's also worked for a number of startups, some of which have been acquired by companies like Qualcomm and TI. So that's kind of what we've done. I think this is startup number 10 for me. Kind of when you get the entrepreneurial bug, it's hard to kind of give it up. So fun stuff. So the company, we are headquartered here in Austin. We were founded in 2020, literally right as COVID was hitting. So fun times trying to raise money when that happened, and the chips, just everything stopped and all that fun stuff as a chip startup. So we're currently way undervalued. Our valuation should be 80 million, but we made the silly mistake to go public on the Toronto Venture Exchange pre-revenue. We may be going private again, we'll see, and then kind of do a Dell, go private and get the product out and then re-IPO maybe directly to the NASDAQ. The idea was, though, while money was really tough to come by and everybody was looking for the next Groupon or SaaS company, there weren't many people wanting to invest in a chip company. So we talked to some strategics and everything, and we said, then the Toronto Venture Exchange met with us and said, you guys would be a great candidate. We can take you public very quickly. You don't have all the Sarbanes-Oxley overhead and all that, and you'll have access to public markets. So we said, oh, okay, 3 months, we can do that. Well, it took a little over a year. We had to have lawyers in both the US and Canada. And by the time we did, the public markets had cooled off. We went public just over a year ago. Actually rang the bell in Toronto, all that fun stuff. But so far, it hasn't done us any favors in raising money. Fortunately, we have a wonderful investor group of mostly, wealthy individuals, family offices, things like that have done most of the investing in our company. A couple small funds, but for the most part, it's been just a wonderful group of investors who back us every single time we need more money. But the idea, by the way, was as a chip company, you don't need a whole bunch of money up front and go burn through it like some of these, .coms or now some of these AI companies are doing. You need money in chunks. Every time you do a tape out, you want to build volume inventory. That's when you need money. So the idea was we would, get the product out, start to drive the stock value up, and then next time we needed money, it would be a lot less dilutive. But again, the public markets have cooled in large part because interest rates are so high. Investors are just keeping their money parked, and they're making crazy money without having to put any at risk. So we'll see what happens, but we're not alone in that space, that's for sure. So you can see here a little bit of some of our partnerships. I actually have a newer version of the slide that talks about the more interesting partnerships are our go-to-market partners, which are Lenovo, Worldwide Technologies, 2CRSI, E4 in Europe, etc. So what are we doing here? And by the way, I want to give you a little background on the company first. Then I was going to tell you about our product. And then I was going to tell you more about why RISC-V. Overview and update on the RISC-V ecosystem and what it's all about, why we chose it. So that's where I'm going with this. So investors want to hear it's a $1 billion problem, only you can solve it. We have that. We're after a $10 billion market, as I'll talk about. But customers do not want to be told they have a problem. Customers, their whole thing is they don't want to miss the next big thing, FOMO, right? Fear of missing out. So I had to sit back and think after doing all the investor calls, 30,000 feet, what are we doing? So in the good old days, the PC came out, you plugged a math coprocessor into your PC and your spreadsheets and stuff just ran faster. It was easy. It worked. Open ecosystem. For the last 25 years, and I'm being generous here because FPGAs have been a lot longer than that. We've been trying to do a C to gates flow. We've been trying to find something else that would help accelerate computing workloads, right? Compute-intensive workloads, be they engineering, scientific, AI, whatever. So the most successful, of course, has been NVIDIA with their GPU, because 2006-07 is when they kind of started CUDA. They hired the guy out of Stanford, who had done this in his dorm room. And they said, let's go try to make this work, make a more general purpose GPU usage, right? The problem with these things is, number one, not many applications lend themselves to GPUs. Talk about that in a minute. But the real issue is you pick your poison. They're all lock-ins. Everybody knew CUDA when they did with NVIDIA. They knew it was a proprietary lock-in thing, but there was really nothing else at the time that even had a promise. So people went down that path. Our DOE national labs in particular really felt the pain when Coral, the first bid, you know, back 15 years ago or whatever, was won by IBM and NVIDIA and Mellanox, but Coral 2 was won by AMD. Not just the CPU, but the GPU. All that code they wrote, all that code they ported to NVIDIA CUDA, flat out doesn't work on an AMD GPU. And oh, by the way, if they did it for an AMD GPU, it flat out wouldn't work on Intel's new GPU. And same's true in your FPGA. You pick your poisons, Xilinx or Altera, completely different. One won't work with the other. So we're back to the other way, because customers, by the way, hate this. Their biggest investment is as any enterprise company, is their software. They're buying new hardware every 3 to 5 years anyway, but the software is the massive investment that takes all that time to build and to QA and ensure everything's right. So we want to make it easy again. We built a compute accelerator that's built for HPC. It's versatile, very versatile, and open, and it plugs into existing servers just like your GPUs or FPGAs do. So here's the thing. If you listen to NVIDIA and Jensen, and again, he was my go-to-market partner at a previous company. I've done lots of joint webinars with NVIDIA. Would never want to compete against them head-on. Not going to do it. You look at the companies that are trying to do it. They're all just a littered waste of hundreds of millions of dollars. GraphCore, Grok, you know, you name it. They're just going down the toilet losing against NVIDIA. So Jensen would tell you that, hey, buy an NVIDIA GPU. The more you buy, the more you save. They do everything, right? Well, no. So it turns out in HPC, forget AI for a minute, we're going to park AI, because again, nobody wants to go compete head on with NVIDIA. You're not going to win. But in HPC, all these applications, yes, they're used on Wall Street for things like Monte Carlo simulations. They're not used at all in, you know, graph analytics or things like that, financial trading platforms. They cannot be used for that. They just don't work. Same too, you hear in oil and gas, oh, GPUs are everywhere. Well, yes, in seismic, when you go to find the oil, but once you've found it, the other half of the problem is then figuring out the most profitable way to produce the oil. And that's reservoir modeling and simulation. GPUs just flat out don't work. It's an all CPU workload. You go on and on, genomics, computational fluid dynamics, climate and weather modeling. For the most part, every now and then there's an exception starting to pop out. But for the most part, GPUs don't work, and we're out to fix that. We're out to address the entire market. So what we've done is we've built what I like to call a supercomputer cluster on a chip. Easiest way to think about this thing. So each of our chips, we've packed almost 1,800 cores, all 64-bit floating point enabled cores on one chip. We put 4 of these chips on a PCIe card, interconnected with our high-speed mesh network. So you get over 7,000 64-bit cores on one 3/4 length PCIe add-in card. So large-scale computing power. This network can support up to 256 of our chips connected, by the way. And not only were we focused on performance, but we're focused on cost, so performance per dollar, and energy efficiency, so performance per watt. This is just unprecedented. I have people tell me, my gosh, I used to think my 48-core Threadripper was pretty cool. 7,000 cores. Holy cow. And you can put how many of these in a server? You know, 8 of these in many servers. So this is pretty massive. And it uses less power than NVIDIA H100. So that's at a high level what we're doing. Since you guys are IEEE guys, a little bit about it, starting to the right. So about 1,800 cores. They're organized in clusters of 64 cores. Each core interconnected with the mesh network fabric. We have 6 DDR memory controllers per chip, 128 lanes of chip to chip. If you do PCIe, you only get 64. It's a limitation of our IP block. One of the only things we bought for this chip, everything else we built ourselves from the ground up. We also have some algorithm-specific accelerators. The fabric that's connecting these, it connects, you know, the chip to chip, and it connects on chip, all the cores, is essentially a Manhattan grid, fabric. We're driving copper as hard as you can drive it, basically, and for high bandwidth, low latency. Then the core itself on the left is our own 64-bit superscalar, implementation of a RISC-V CPU core. It's got multiple issue out of order. We implemented variable instruction width. We support vector, SIMD, and tensor. And we even did some mixed precision floating point for some AI workloads, even though that's not our initial focus. Tightly integrated memory and core-to-core fabric. Each core has 64K of cache. So 128 meg, of cache across the chip, which I used to think was, it's okay, 64K of cache. I learned last week at the HPC AI Wall Street conference that the NVIDIA GPUs only have half a K of cache per core. So 64K of cache per core is pretty good. And again, this works with a thriving RISC-V open software ecosystem. So I'm going to jump. I didn't put this slide in here for y'all, I guess. I kept it out, put it in the backup. So why are we going after, I kind of talked to it, but the reason we're going after HPC first is a couple things. Because everybody's after the bright, shiny object of AI, right? So it turns out the accelerator market is just the compute accelerator market is $168 billion a year, growing at about a 25.5% compound annual growth rate. Now, Lisa Su said at their AMD meeting last month, at their annual meeting, that they see the accelerator market doubling next year. So forget the 25%. The point is, it's a fast-growing market. It's very profitable, very lucrative. The problem with AI, we're treating that as later upside, because I kind of said everybody who's competed against NVIDIA has lost. You have to be on the very latest process node, so your tape-out cost is $15 to $25 million just to try to play. And GraphCore raised $730 million, boom, done. Grok $300 million, done. Esperanto's trying. There's a lot of companies trying, but even Google, who invented, they're on their 5th generation of their AI chip, their TPU. They invented TensorFlow. They invented the transformer technology behind, ChatGPT. They had to buy 26,000 NVIDIA GPUs because it wouldn't work. So, it's kind of a crazy, it looks attractive at first, but it's a crazy market to go after. The other problem is most of the AI is done in the cloud. And even if a hyperscaler wants to implement your solution, I actually have the CTO of one of them on my advisory board. He told me it'd be 3 years before they could do it because the scale they're at, their worldwide data centers, they'd have to look at their power, cooling, servers, rack space, everything across every region of the world. Then they'd have to modify their software stack to support. Then they have to train their people. And it goes on and on and on, right? So trying to go after the hyperscaler market and all that stuff sounds great, but as a startup, you'll die. You'll never get there. Turns out the HPC market is very different. It's growing fast. It's very compute intensive. It's only about $10 billion, but I'll take 10 billion to start. Not only is it highly compute intensive as some of those apps we showed a minute ago, but it's almost all open source software, over 75% of it. So you're not having to go pay ISVs and beg them to port to your platform. And oh, by the way, almost all of it is done initially, at least in their own data centers for fast adoption. So you're not having to go deal with the cloud hyperscaler. And they're always looking for a better mousetrap. Anything that, Shell can use to beat BP or ExxonMobil, they're going to go do it, right? Anything that, pick your diesel engine provider is going to run their CFD faster, like Caterpillar instead of, Detroit Diesel or whoever, John Deere, they're going to go do it. So HPC is a really nice sweet spot that, frankly, the other problem is the GPU guys are ignoring because they can't sell enough GPUs because of ChatGPT anyway. So they're converting more and more of their cores on their GPUs to low precision cores. Dan Stanzione, who runs TAC here in Austin, back in March at the RISC conference at Energy HPC, in his keynote, he made the comment, not all of our code needs to be double precision, simulation. We could do some FP32, but FP16, FP8, give me a break. At some point, you're just guessing. Why run a computer? I talked to my Total Energy friends over in Europe earlier this year, and they said, oh yeah, we call GPUs random number generators. They're just not that useful anymore for HPC. So So that's the deal. We are not giving customers yet another GPU. As one industry analyst said, you know, the subquote up here, what customers always wanted. That's what he said. He stopped me and said, you realize what you've done. You're giving customers what they've always wanted. For 10 or 20 years, this is what they've wanted, a massive amount of CPU cores and memory, right? Don't make us completely rewrite our software from scratch, only to find out that it didn't even work, you know, or had minimal impact on the GPU anyway. So that's what we're doing. So then it gets really interesting. About 2 months ago, so first of all, okay, more applications. We can go after a lot of things where GPUs just flat out don't work or never will work, right? There's a lot of codes that just depend too much on core-to-core communications. GPUs stall. So we'll go after that. The high-speed, low-latency core-to-core communications, turns out, is a very significant thing for very predictable performance. That in our MIMD architecture, had a gentleman who used to be my customer when I was selling Opteron-based servers back in the day on Wall Street. He ran all of the HPC and mission-critical systems for Credit Suisse. He just stopped me when I got to this slide and said, Doug, stop. One word, determinism. What you guys have done here is you have built something that can absolutely be deterministic. And I said, okay, so determinism means, right, if you give, you know, an accelerator computer, you know, the same input 5 times, you get the same answer all 5 times. You don't get 5 different answers. You know, think about when you're doing a big multiplication addition and you're moving the parentheses around. That's what happens in a GPU. You'll get very different answers depending on the order of how they go through the GPU. And I didn't fully appreciate this, so I went and talked to our CTO, and he said, oh yeah, here's the problem. And I finally was able to come to a picture for it. So in a GPU, this is an NVIDIA one, they're organized in these units called SMs. Each SM has 128 shader engines in it. So each SM, all 128 shaders have to act upon the same instruction. They just can do adjacent rows of data. So if it turns out there is no adjacent row of data, you got 127 shaders doing nothing. But even if an SM wants to talk to the SM next to it, it has to go to cache. That's 100 to 200 clock cycles, just even if they're sitting right next to each other. With our architecture, if you've got, you know, a CPU core talking to a CPU core next to it, it's a clock cycle. Across the whole chip, it's 6, maybe 8 clock cycles. It is just night and day, and it's completely predictable. So it turns out this means, in addition to all those other applications that don't even fit a GPU, there's other applications where GPUs are disqualified. So this talks a little bit about, you know, SIMD architectures are easier to build, but MIMD architectures like we've built, right? Each instruction has its own data pool. They're harder to build, but they can do a lot more things. And the fact we can run Linux across this thing, or, you know, one API, SICK, or whatever, but we can also run real-time operating systems on this. And you can get down to bare metal, and we even support the atomic instruction set of RISC-V. So we address this. So what does that mean? It means we can be used in real-time, real safe computing where GPUs are disqualified. Flat out not allowed. So things like the trading floor on Wall Street, things like smart weapons, surgical imaging, like the Gamma knife for brain surgery, self-driving cars, things like that. Thunderbird can be used for, right? And even if it's maybe only one chip driving, you know, a self-driving car, maybe even only 500 cores, maybe we scale it down. We've talked to some of the tier 1 OEMs about this. It can be used for a lot of these workloads. So this turns out to be a really big deal. And it was a big deal last week in New York at HPC, now at Wall Street, because all the big banks know this. They've all tried to do CPU architectures, GPU architectures, and with the various scheduling algorithms and the level 2 cache, level 3 cache, and all that, they just flat out don't work. And they've had to try to use FPGAs, but for a lot of these implementations, it just takes too long, and it's not worth coding it up in Verilog. Because we all know when you build an FPGA, you're effectively building a prototype chip. So that's a bit about where we're going, what we can do with this thing. Why is this not going? Okay. So the other thing we've done is to keep the power down and the cost down and everything else, we have kept this thing to a half a reticle. We originally thought we could get 3,000 cores on each chip, but the constraint we put ourselves to be a half reticle, unlike what all the GPU guys and everybody else do at full reticle, that kept us down to only 1,800 cores. So you guys probably know that's a nonlinear relationship in terms of yield. So it gives us a 70% cost reduction as well as lower power and latency. So that's another smart thing the team did from the get-go. The software ecosystem, we leverage the very rich established RISC-V software ecosystem. It's been out for 11 or 12 years now. The last 6 or so, it's really taken off commercially. I sit on several RISC-V organizations. So does our principal software architect. He actually leads one of the technical groups. And we do this to be looking ahead at the roadmap and what's coming and where the gaps are so we can be addressing them, because we don't want to invent anything new. The GraphCore guys famously said when they were coming out with their AI chip for vision that, we spent 6 months thinking about the software stack and what we would build there before we even thought about doing the chip. Well, that's great, except back to that problem that enterprises' biggest cost is their software. What that means is they're trying to have to evangelize and sell people on their software stack, even though, TensorFlow and PyTorch are at the core of it, but they've added all this stuff around it that you have to do to make it work. So now you're betting on a startup. You have to then sell them on it, train them on it, get them going, the whole thing. It's painful to get going. And, if you go away or somebody buys you and puts you out of business, like maybe NVIDIA feels you're a threat, well, then you've wasted all that time. So our whole goal is to use a standard CPU programming model. So you don't need CUDA, you don't need ROCm, SYCL, any of that stuff. It's back to the code you used to write before you had to go down that path. Standard compilers, OpenMP, MPI, etc., all that kind of stuff for highly parallel systems. And with RISC-V, the key things are there. So we have, the normal GCC, G-Fortran, GDB, and all that. There's also high performance LLVM-based compilers that our federal government's actually funded NVIDIA, by the way, PGI, to go write them for RISC-V. And all the standard HPC libraries are there, that you would expect, as well as key operating systems, Linux and RTOS and those kinds of things. So you got a good question here in the chat about from Ron Waters, what are the appropriate benchmarks and how comparatively do you perform? So I'll get to that in just a sec. So we're in the process of taping the chip out right now. We finished our dry run tape out last week. So we're going through the actual tape out right now in the next couple of weeks. And, then it'll go off to TSMC to be fabbed. And we'll get chips back end of the year, January timeframe. In the meantime, we launched an early access program to try to accelerate the S-curve, right? We wanted to get, early access partners clicking off, hopefully somebody in each of those categories of things that just are kind of low-hanging fruit because there really aren't GPU solutions to work with. So early national labs, our friends over at TAC and other places, some key OEMs and everything. So they get the early hardware. We give them an emulator initially. In the spirit of the Thunderbird legend, we've called it Thunder and Lightning. Thunder is the emulator and Lightning is the early card when it comes out with the chips on it. And we support the heck out of them, and they pay us some money to help cover the support and the cost of the hardware and everything and get going. So we're working on that. We've still got a couple openings in the early access program. I'm really trying to find the right Wall Street FinServe company to come, fintech company to come on board. It's one reason we were in New York last week. And it looks like we have 3 candidates for that. So this kind of sums it up at a high level, and I'll get to some of the benchmarks and numbers here in a second, schedule. But at the end of the day, we're looking to disrupt on every level. We don't just want to be, more versatile and everything. We want to be, lower power, lower energy consumption. It turns out it's about 150 watts a chip. We can scale this up, and we're going to come way under. If you can even find an NVIDIA H100 right now, they're going for like $48,000. We're going to have a 2-chip card at $6,500 and the 4-chip card at like $11,000 list price. So we plan to just disrupt at every level. And I've heard a few of our customers tell us that, my God, some of these companies aren't going to know what hit them, because we're doing what our Dell friends love to say. We are truly democratizing HPC and AI with this solution. In fact, in my role, the Society of HPC Professionals, we had Cerebras, engineer from Cerebras, come on and talk to us about their, wafer scale integration, their monster chip. And, you know, at the end of the day, we're kind of building a small version of a Cerberus, you know, a democratized version. You can buy it in bite-sized pieces versus, you know, $2.2 million a chunk. So, so that's what we're doing here. And by the way, even the Cerberus thing, it's pretty good at HPC, but it's really focused on AI. So right now we're fabbing this initially. The Thunderbird will go out at 12 nanometer. We've got all our wafer and substrate capacity secured. The next spin of the chip will probably be at 4 nanometer. We actually did a 5 nanometer test chip. So we have access to all the latest TSMC processes and libraries. That took a lot of doing, but when they saw this team, they saw what we were doing, they said, okay, you're the type of company we like to bet on for the future. So we did this. Not many companies can get a 5 nanometer chip working first time out the gate, much less a company our size, only about 20 people. That's kind of unheard of. So we think we can get a lot more stuff on the next version of the chip. And that's the other reason to have the early access program, is to have the right partners giving us the right feedback of what needs to be in the next turn of the crank. So, this is the schedule I kind of just talked about, taping out and getting stuff back into the year, Q1, qual, do all that kind of stuff, and ramp production through 24. Really focus initially on HPC, especially things like CFD and reservoir modeling and simulation and weather, climate, genomics, those kinds of things. We chose DDR memory, by the way, for this first chip after a lot of outreach to customers. The common theme we heard back was, you guys made the right call. If you were focused on AI, you would have to use DDR memory. But since you're going after HPC, we'd rather have more memory than faster memory. So we know that's going to be a bit of a bottleneck the first time around. That's why another reason we're not going after AI off the bat. But we know people are going to use this for AI augmented HPC. And the graph analytics guys are going nuts over this. They're all about CPU cores and memory, and they're like, you could not have built a more perfect chip for graph analytics, which is getting to be a pretty big deal for fraud detection. Turns out that's what our intelligence community people typically do to find the bad guys. So a lot of feedback there. Then Thunderbird 2 design starts right on the heels of that. As I said, we've already done a test chip. We're looking at 4 nanometer, maybe 3. Feedback, we could quadruple the core count to almost 10,000 a chip. We've had some feedback already from some, like in the intelligence community, that we like your core count, but you might want a little more cache memory per core. So that's the type of feedback we'll get. We know we'll do HBM memory this time around. The other problem back in 2020, 21 with the chip shortage was HBM memory supply chains were very sketchy, to say the least. Not a lot of sources, and we did not want to be waiting in line behind Apple, Qualcomm, NVIDIA, AMD, whoever. So, but this time around, HBM is getting pretty common. So, and then we'll do even more feature build outs for HPC as well. So, performance. Where we're at, jump to that slide down here, and then we'll get to RISC-V a little bit. Sorry, I got it. So, what we're seeing right now is about 8 teraflops a chip. We see headroom to get to 12. So on each PCI card, that's 32 teraflops right out of the gate on the PCI card. We really think we're actually more like 75 gigaflops per watt, but when we put in writing, we like to, set expectations a little lower so we can exceed them. So that's pretty impressive. That performance per watt is half of an NVIDIA GPU. So, and we again think we can do better than that. We're taping the chip out now. We've got an emulator. We're starting to run some benchmarks. These are the 2 we're focused on initially for a couple key reasons. Some of our key applications. Our early access partners are going to be running lots of benchmarks on this thing initially on the emulator, and they can get some pretty good extrapolation with that. And then later on the full chip, of course, when they get it. Plus, they're porting a lot of their codes to it. So I will pause there before I go into RISC-V and certainly take some questions. I see one of them here from Luis. Is your design teams local or spread out? So we're actually, headquarters is here. Most of the people are here, but we actually do have, you get the talent where you can get it. Our principal software guy is in Atlanta. He used to work for AMI doing BIOS stuff, and he worked for Sun before that and Oracle and things like that. One of our key layout guys is in Maui. We were very concerned when the fires hit, but luckily he was not affected, didn't even lose power. He had a pretty major road between him and where the fire was, so it was a fire break. And we got a really super smart guy in Idaho. He's won the Intel's highest award, the Intel Achievement Award, twice. So, everybody, the servers are all here in Austin. Everybody VPNs in and runs on them here.
Great. There is another question by Ron Waters that you might have covered about benchmarks and performance.
Right. Yeah, that's what I just did. I jumped to that slide on it because, again, we don't have the chip back yet. We will be doing, again, with the emulator, we're going to get more and more results. But early simulation results and everything, which are, cycle accurate and everything, are showing those kind of numbers. 8 teraflops a chip and really about 75 gigaflops a watt. Let's see, my friend Bob asked a question. Is the memory coherent? So, it's obviously going to be NUMA effects in this for programming, but we do have one consistent, contiguous memory segment for this all the way, not only across the chip, but across up to 256 chips. So we've tried to make it as easy as we can on the software guys. There's still going to be a lot of work. Some applications, by the way, are going to love this, and some are going to have a hard time, I think, because some of the guys have told us they love the fact that we don't have an L2 cache, because it's a much more performant system, and a lot of their kernels will fit in the 64K of cache, and they don't have to fight the LRU algorithm constantly kicking them out, of the local cache and try to reload the cache and all that. They can just pin them there and run. So that's going to be good. I see Daniel raised a hand. Feel free to chime in.
Can you hear me okay, Doug?
Yeah.
Great. I love the product. This is great, and I love it that you're kicking kicking the industries in the behind. My question for you though is the types of applications that I might consider for your product would be ones that don't involve a lot of bandwidth. Would that be a fair assessment? Because it seems like the bottleneck is the PCI bus that you're connected to for thousands and thousands of CPUs would be a huge bottleneck unless you can just compute in place. Is that sort of the right model in my mind?
Yes and no. So if we have to go to PCIe, obviously, we're constrained by that. But the fact that you offload the work to this and you have 7,000 cores interconnected without going through PCI, once they're on the card, it's all our mesh network directly connected. So very low latency, high bandwidth. The initial load's going to take a little bit of time, of course, and then data back out, I guess. But once it's on the card, you're running. The other thing is we have one of our OEMs has a 2-tier server model, right? That's got one tier, it's the x86 complex, for storage, networking, and all that. Right. And then the other tier is a sled of accelerators. So they've got one today for the NVIDIA GPUs, AMD GPUs, whatever. They also want to build one with our accelerator. So if we can put 4 on a 3/4 length PCI card, they think they can put quite a few on that server sled. And you reach a point where how many cores can your application really use? I've seen some pretty big graph databases, but not a lot else. It's going to be kind of this massive, really.
Right. So even as long as the band, because 7,000 CPUs, you can imagine that could be a huge amount of communication in some incorrectly designed systems. But if there's just a whole lot of number crunching going on with a slow trickle of data, that's probably that I believe is the best model. Is that right?
Well, again, you got the cache, you got 120, you got 64K of cache per core. That GPU only has half a K. So we're giving you 128 meg on chip. Then we're giving you 6 DDR memory controllers, so about another 48 gigabytes per chip of DDR, right? Right on the card. Each chip. And by the way, each chip can access DDR memory off of other chips. If you only need all the cores on one card, you can actually, they can each grab the memory from the other. Now you have more latency to get it. You got to go through a little more long, but again, if all the chips are pretty much local, it's going to be pretty quick. It's not HBM, so it is DDR. But that was the idea: more memory, not faster memory. We heard it consistently. So, so.
Well, I'm wishing Yeah, wishing you a lot of success, because this is a leapfrog product, and it's going to
Yes.
it's really going to make computing, democratize computing. As when can I get my board? That's my
Probably Q2 of next year, unless you're going to join the early access program with a good
Yeah,
application to get on board. So.
I'm more of the consumer guy. I'm the hobbyist researcher that doesn't have the deep pockets that other customers that deservedly need to be first in line.
Right. Yeah, we heard that from a number of the key application engineers of some of our OEMs. Like, I'm chomping at the bit to get one, right? So
Yeah.
So I know, I get it. Yeah.
Thanks for presenting.
No, I appreciate the good questions. I'll go into RISC-V in a sec. All right, so here's a question. How do you envision AI enhancing HPC given HBM? Also, who are your external storage partners? Okay, so I'll do the storage thing first. We don't really have a storage partner. We're working with some big OEMs. I mentioned several. We're on an NDA with all the other big ones I didn't mention, like Dell, HP, IBM, everything. They're very aware and very interested in what we're doing. They just aren't typically the first to go. But they have some storage offerings and stuff. But for the most part, we're really just worried more about the memory that's going to be on the cards and everything, where we're getting all the DIMMs from and everything so far. But certainly, I've met with guys. I know, been in this industry a long time. I know the guys at at Dell because of my EMC connections, at Pure and some all the other NetApp and all those. I got guys who used to work for me who now work at Pure and NetApp and places like that. Yeah. But how do we envision AI enhancing HPC? It's really not an HBM thing, per se. I think the biggest thing is I'm not going head on after pure AI workloads. The interesting thing, though, we're keeping an eye on it, is the ChatGPT thing, right? OpenAI. So there's a group out of Stanford in partnership. I got to look it up. There's a university in Canada, in Ottawa, that's again a well-known AI university, and they in Stanford looked at what the heck is it in ChatGPT that's causing this massive exponential drive in compute performance. What's doing that, right? And they found out that it was actually in one of the commands in the transformer library. So they replaced that with the convolution. Turns out we have a convolution engine on board this thing. This thing's going to be pretty kick butt for FFTs, which are a lot of codes. And if it turned out Hyena comes out to be the big thing and not ChatGPT, we may be even busier than we thought. But everybody's adding AI to all their codes. I've been presenting and running panels on generative AI and HPC and everything for the European Oil and Gas Association, energy people, the SEG here, and others. Everybody's adding AI to everything. They're either doing some AI pre-processing to minimize their data set of what they have to simulate, or they're doing AI post-processing at the back end of the simulation in some way. And we're actually in kind of partnership with a couple of pretty well-known AI companies that want to work with us because they do have a simulation component. So, there's going to be work just because of data gravity. I think there's going to be some cases where people go, well, let's just go ahead and while it's here, let's now run the AI on it on this thing, because this is it may not be as fast as, an H100 for running the AI, but, it's all here. It's pretty fast. Let's try it. So I think we'll see some of that. And then, of course, HBM next time around. So Bob asked the question, if a processor in the northwest corner modifies data also held in a processor in the southeast corner, how much chatter is created? So it turns out RISC-V and the way this works is pretty interesting in this regard. It has a model where I remember how our CTO phrases it, but it's basically as soon as the code's modified in the processor, it's immediately locked. So you don't have to wait for it to write out to cache or this or that. So that's an inherent benefit in RISC-V that lowers that chatter and again lets it do atomic operations and things like that. Kai said, is AMD your closest competitor? I would argue, well, maybe, with the new MI300, I guess. Architecturally, our closest competitor is Esperanto. They put about 1,000 cores, RISC-V cores, big and little, on their chip, but they focused on AI inferencing. In fact, their chip's only 25 watts, very low power, lower performance, low precision math. We don't do that, right? So we went the other way. And in fact, a good friend of mine is an industry analyst, and he told me that Esperanto kind of realized the error of their ways. They went after the shiny object of AI, and they're realizing the real money's in HPC. But he said it's going to take them 2 years to catch you guys. because everything's low precision, no vector support, no nothing. So different market. But RISC-V, good stuff. We like them. All right. We'll pause there. You guys think of some other stuff, we'll come back, but a little bit on RISC-V. And I owe special thanks to Christy. He's the original professor at Berkeley who came up with the idea to do this. As you'll see, many of these slides are his, kind of reformatted or borrowed some of his stuff. He's also the chairman of the RISC-V Foundation and on the board now, RISC-V International, and also the chairman and CEO of Sci-5. So why RISC-V? So this, if you look at open interfaces, they've been accepted practice in everything we do, right? You look at all these different categories, there's open standards in everything except hardware ISAs, instruction set architectures, right? We have POSIX for OSs and threads and stuff. We have, C, C++ compilers, SQL is a standard, and, MySQL, Postgres. There's not only open standards, but even free and open implementations of all of these, right? Except for ISAs, right? You have proprietary implementations, things like x86, ARM, IBM 360. There's no open free. Why not? So the important thing to know here is it's not necessarily the ISA's fault. Some companies just do bad business and go out of business, like our friends at DEC. If somebody would have told me, 20 years ago that the number 2 computer company in the world would be bought by a PC clone company, I'd have laughed. Most people would have. Some great architectures, the VAX, the PDP-11, Alpha, right? Intel, they're not immune. They have a kind of a graveyard of dead ISAs as well, right? Never forget AMD knocking Itanium out with x86-64. Spark, again, it was like the dominant thing for the longest time. Everybody was trying to beat Spark. When I was at Cadence and running the platform business, HPE, IBM, DEC, everybody was begging me to have us be their development platform instead of Spark. They opened it up as a standard, but it's all been closed down. MIPS, who would have guessed? MIPS was in every laser printer, avionics, everything, right? MIPS is now a RISC-V company. They're doing RISC-V implementations to compete with Sci-5 as a service. IBM Power, many of us, RS-6000 number 2 went with me on an airplane. I put it in Northrop Research. I helped them port the 3D CAD system to it after living with the RT for years and years. They tried to open it up. Yeah, it's crickets, sadly. And then ARM, right? So we all been found ARM. They just IPO'd. We're all wait and see. But at the end of the day, you still, unless you're one of a couple of companies like Apple, you're not going to be able to modify that instruction set. It's proprietary. You license the IP and you lay it out. So why would you entrust your software investment to a proprietary ISA? Again, it's your biggest investment as a company, and certainly as an ISV if you're selling, commercial software. So the other interesting thing that happens, and you look at an existing system on a chip, and this is an older one. This is an NVIDIA Tegra. It's gotten way more complex since then. There's typically an application processor like an ARM, right? Graphics processors, image processors for the camera, things like that, radio DSPs, audio DSPs. So you'll have a dozen ISAs on some SoCs, each with its own software stack. Many of these are not even supported. It was some, embedded engineer who did it. He had to do it. He, software stacks aren't exactly his thing, but he had to do it to get it done and get it out the door. And, there are typically chunks of IP that are bought, things like that. It's just kind of interesting, and there's just not a great reason for it if you do it right. So what if there was one stable, free, and open ISA everyone could use for everything? That's the whole premise. So how RISC-V started was back in 2010 at Berkeley. After many years and many projects using MIPS, Spark, x86, everything, they needed to choose an ISA for the next set of projects. The obvious choices were x86 and ARM. We had the same choice, frankly. x86 is just impossible. Too complex IP issues. In fact, if you look at what we're doing, a couple of our partner CEOs have called what we're doing building a Xeon Phi on steroids. It's probably true. It really is, actually. The problem with Xeon Phi, they had the right idea, a massive amount of a relatively simple core. Their problem was their relatively simple core was Pentium, and actually later P6. The most they ever got was 72. That's not a massive amount. That's why it died. That and some really dumb implementation mistakes they made along the way. ARM is mostly impossible. They didn't have 64-bit back then. There's IP issues, complex, the whole thing. So they started this, quote, 3-month project during the summer to develop a clean slate ISA. And Christie was one of the guys, and those other key people there. Took 4 years later, after the 3-month project, they released a frozen base spec. And again, just the base minimal set of instructions, lots of tape outs and research pubs along the way. So it was named RISC-V because it was the 5th major Berkeley RISC ISA. So don't say RISC-V, say RISC-V. All right, so RISC-V International was formed, RVI as we sometimes call it. And it's a nonprofit entity. They actually moved the headquarters from the US to Switzerland to be as neutral as they could be and global as they could be, right? And it's all about just accelerating RISC-V adoption. So it's a free and open instruction set architecture, right? But of course, people are free to build their own chips and their own customizations on top of it and everything else. So they help, keep us all together and drive things to convergence is kind of the key. So we have various monthly meetings, various different SIGs, various horizontal and vertical, groups, et cetera, driving various things for embedded, for data center, for automotive, for space, for HPC, you name it. We've got groups driving unique standards and everything for this. So the beauty of it is it's an open standard, right? It gives you freedom to innovate. So, you've got all these kinds of things going on, right? And this is just a snapshot in time a while back. The latest is up on the RISC-V website. They've actually got a couple different maps that have come out now of just to try to keep track of it on the website. But needless to say, there's a lot of people behind this because it just makes sense. And by the way, a lot of these cores are companies that build their own stuff in-house. So, for example, the latest Google TPU, the version 5, swapped out ARM cores for the controller cores on it with RISC-V cores. Western Digital, they've taken all of their ARM stuff out and they're replacing all of it in their disk drives. It's all RISC-V now. In China, it's taken off fast. Alibaba, Tencent, Huawei, everything they're doing is based on RISC-V. And of course, it wouldn't be a Zoom if that didn't happen. So yeah, it's got a lot of momentum behind it, to say the least. Why is it popular? Engineers sometimes don't see the forest for the trees. That slide earlier where they drop a block of IP on, a block here, a block there, a block there. It's all about the business model. It's not happening because something ran faster or we're mad at Intel or anything like that. It's a new business model. It changes everything. You pick your ISA first, then you pick a vendor or you build your own core, right? If you can actually do hardware software co-design, which in HPC is a huge deal to be able to build custom stuff. Same with IoT. If every little, millijoule counts, if you can design your own very low power core versus taking what you get off the shelf from ARM, you can have a more successful product. And the fact you don't have to pay a royalty on it, well, that's nice. Although, you may spend more time engineering it yourself in the first place, but that's the key, is it's an open business model. So if you compare the business models, right? x86, chips, yeah. ARM, yeah, many of them. RISC-V, yeah, many vendors. Chips, you only get 2 vendors right now, right? Really, at the end of the day, it's Intel or AMD. They're both great, but you are limited. Architecture license with x86? No. Commercial core? No. You can't. No. Right on x86. With ARM, you can get an architecture license, but only a couple people have been able to afford it. It's a very expensive proposition and very restrictive. Is there commercial core IP? Yep, from ARM. That's it. Right? You take what you get. Add your own instructions? No, unless you're one of those architectural licensees. Open source? No. With RISC-V, yes to everything. You can get it. Everybody has an architectural license. There's commercial core IP from many vendors. Can you add your own instructions? Absolutely. That's what we've done with ours. Is there open source core IP? Yep, many choices. So that's really why RISC-V is succeeding. In fact, this chart reminds me of one of my favorite comments I make when I talk to people. They talk about ARM and how they got billions of installs and all this. Yeah, because it's in all these cell phones we have, right? Well, that's one of the first places that RISC-V vendors are targeting, people like Qualcomm and others, right? Even Apple's got RISC-V projects going on. Because frankly, ARM has become a tweener business model. If you look at this, there's chips, massive ecosystem, everything for x86, right? You buy chips, you buy systems. When I was working for an ISV, I could go to, pick my partner and say, help us, pay to port our software to your product. And it would be like a Dell or an HPE or an IBM or whoever, and they do it. I go to ARM. When I did it, they're like, well, you got to go talk to our licensee. So I have to go talk to Cavium. I have to go talk to all these other people. And every one of them was doing something different with different core IP. There was not one port. x86 was easy. Software vendors kind of like that. ARM, turns out, was pretty tricky. And even then, you had all these restrictions. And you're like, why? With RISC-V, it's all open. It's all easy. And the way they've orchestrated the instruction set, I don't think it's in this slide deck, but they've built kind of a stack. So there's a base implementation of like 55 instructions that all RISC-V processors have to support. And then there's what they call profiles on top of that, where there's like a data center profile, there's an HPC profile, the atomic instruction set profile. So the instruction set grows and grows and grows, but all RISC-V processors have to be able to boot the basic core. And then you can tune things, to the profile. So now you've got a common set of things that the software vendors can write to. They know those instructions will be there because you're supporting the data center profile or the HPC profile. So it's fresh, it's modern. ARM's been around for over 20 years now, and RISC-V is really where it's at. As we say, it's inevitable. Industry wants this business model. We're going to have the best processors in RISC-V. It's just inherently a better, more modern ISA. You don't have to boot DOS, right? x86 still has to boot DOS. Many people don't know that. You're going to have more vendors competing for business, more cores designed. You're going to have the best ecosystem. So that's how we see it going. And it's an inherent sustainable. Oh, here's the base plus modular extension. So that's the profiles. So that's why this, really technically is a wonderful architecture. You don't have all the legacy nonsense that's in so many things. And it's community designed. There's input from leading experts and not just industry, but academia as well. Lots of universities are doing stuff with this. And again, for HPC, it enables hardware software co-design. Plus offering this stable long-term platform that's not dependent on one vendor, staying in business or two vendors. It's a global standard. Not any one country owns it. You get very efficient standard scalar processing and vector processing. So it's just it's a great match for HPC in particular. So that's what I had. All right. So here's something. Perhaps transformers for workloads is a way to spread all those high precision bytes across internal and external storage. Yeah, maybe so. Again, we're going to be looking for a lot of feedback from some really smart people in our early access program who are on the leading edge of many of these things to help give us that feedback.
So all welcome to unmute themselves and then ask questions.
Yeah. Covered a lot of stuff, I know. A little bit of a fire hose, but.
So it looks like you did not present the whole thing, right? Can you send me a copy of your
Yes.
PowerPoint or in PDF form?
Yes, I will. I will send a PDF to you, and you can share it to the people for sure.
Okay, great. Okay. Yeah, sounds very interesting. Well, it looks like you're the first in that market.
We are. I'm kind of amazed. The timing is, I've been in this market for a long time. I have a friend of mine, very good friend. Our kids grew up together. The whole thing, the street over, was the architect on AMD EPYC. He's now retired, and living out in the lake and all that. They brought him back for a year after he retired to consult again. But, he told me a number of years ago when they really kind of came out and kind of hit the home run, he said, if somebody came to me and told me that we would come out with an architecture that would beat Intel and do it at a time when Intel completely misexecuted, I would have laughed at him. I would have never believed him. And that's kind of how I feel about what we're doing, right? The the GPU guys are being pulled so hard. You can't even, the wait for an H100 is over a year now, more than a year. And so there's a massive, GPU constraint right now, and they're all being pushed harder and harder and harder to this low precision math and integer math for AI. I mean, some of the stuff in AI now is 4 bits or 2 bits. It's getting ridiculous. And, that's where the massive volume is. And here we are with a, when industry's saying, woe is us, what will we do? We're going to bring, an all CPU, 64-bit CPU solution to market with all interconnected cores, which is what they've just always wanted. So I feel very kind of amazed that our timing is so good.
Yes.
Okay. Maybe this is me. Oh, video available afterwards. Okay. Yeah.
So Daniel Peters raised his hand. He can unmute and ask a question.
Thank you. Doug, can you hear me well?
Yes, sure.
Great. I might have missed it, you might have mentioned it, but is there a rough comparison for the Thunderbird CPUs in terms of where would I put it on the Intel scale? Is it an Intel i9 at 4 gigahertz, or is it, or each one of the, is it at an Intel i3 at 1.2 gigahertz? What sort of rough comparison can I make?
That's a good question. Never thought about comparing to x86 because there's so much things an x86 has to do to be a system processor that we don't as an accelerator, right? I mean, all I can pretty much tell you is take eight teraflops and divide by 1792 maybe and compare that.
Okay.
Yeah. It's a different model. I mean, really, what's the interesting thing that our early access partners are all telling us is they're really excited about the utilization. They said, if you look at a GPU, you're lucky to get within 2 orders of magnitude of the peak flop number that they say they can deliver. And because a lot of those cores aren't even, they're tensor cores or things like that. They're not even really pure cores. And then they've got this whole problem with the SIMD architecture and stalling the pipeline and things like that, right? It just depends. With our highly interconnected, cores, they think we're going to get much closer to the peak numbers that we state. So it remains to be seen. We're chomping at the bit to find out ourselves.
So things that are floating point, 64-bit floating point preferred would be better for your processors. Is that the right understanding? Yeah,
I mean that's our target market. Everything we've done on this is 64-bit flop, right? And they're all 4 wide, multiple issue. So we initially had an 8 wide core too, but it turned out the 4 wide was fast enough and gave us a lot of vector-like performance. So it's 4 wide by 64 bits. That's pretty good.
Yeah, absolutely. It's a floating point screamer.
Yeah. So that's the focus. One of our CGG, it turns out, over in Europe, they're a big provider of seismic and oil and gas modeling, simulate services and everything to all the super majors. Everything they do is 32-bit actually. They do that for energy efficiency actually. In Europe, that's kind of their bent. It's good enough for what they're doing and more energy efficient. We're going to run the benchmarks 32-bit as well for them and see how that comes out.
You get a speed improvement when you chop down to 32 bits? I mean, I
think so. But we'll see. It might, I don't know if it's going to make memory bandwidth worse or better or what's going to happen.
Right.
You're always chasing the balloon somewhere, right? We know this version is going to be memory bandwidth for some apps, but we'll see.
Okay, thanks.
Good questions.
So when you say you ramp up production, is everything done by TSMC and his subsidiary, or?
Yeah, TSMC and ASE. We're happy ASE is the package. They're the world's leading package and test group too. Thomas knows everybody, every corner of the world, right? So we're sure that. Well, you don't get to pick, where you fab. You give it your design to TSMC, and they pick which fab they put it in. The new fab in Arizona, it sounds like it's a little delayed now. It might be 25 instead of 24 or whatever. But but that's going to be 5 and 4 nanometer anyway, and we're not going to be there yet. So I'm sure we'll be initially in Taiwan. We've talked to Samsung. Early on as a backup. We're very concerned about the geopolitical considerations too. Like I said, one of the intelligence agencies have asked us if we would consider a U.S. fab. So, luckily we are at 12 nanometer for this first chip. We were going to originally be 6. And we looked again at the supply chain constraints back in 2021, and we said, yeah, we don't want to risk that, right? We got to get this out. We don't need to be on that leading edge just yet. So by sticking at 12, we could also run this at Global Foundries, which we've done fabs at before, or even Intel. So we'll see. We've got some backup plans. We don't want to do it because it's a whole nother tape-out, a whole nother mask set, and all that. But, for the right customer or things go south, we have plans.
So basically, this is a single chip, then you put a array of product on a board, or is there some kind of chiplet kind of approach?
Not chiplet, it's an SoC.
Okay.
So my friends over at Tens Torrent, I know the COO and some of them pretty well. We're looking at partnering with them because they're doing a RISC-V chiplet plus a GPU chiplet. It's a GPU. We're not doing a GPU, so we're not competitors. And as Keith says, it takes a village. We're all taking on the giant of NVIDIA, and it takes a village. So same with Revos. We've talked to them and a couple of the other guys. We're all in this together. But I told Keith I thought they were a little early with the chiplet approach, and he's thinking, yeah, they might be. The other thing is, for us, it buys us nothing. Since everything's all interconnected, it's all homogeneous. We don't have heterogeneous products. There's really no reason to do a chiplet. It helps you for yield. It helps you if you have one product maybe at 12 nanometer and the other chiplet at 5. We just don't have that issue. And if you look at what Intel did this last time around, for the latest processor, they actually went from a chiplet back to an SoC. Better performance. So for now, we're saying SoC, and we'll probably, certainly the next spin, I think it'll be an SoC as well, but probably more 3D because that's where TSMC and the industry are driving hard.
Yeah, right. Well, it depends on space. You have enough space for your chip, then why bother to go with chiplet?
That's right. And HBM, right? The HBM is really where they're putting focus on 3D initially. So you just go straight up with it. You don't have to, take up 2D area.
How about your plans for growth? Do you have openings for people that might be interested? Do you have needs for new engineers?
Thank you. Yeah, good question. We do. We're always kind of looking to hire the right guys. Lately, we've been hiring more software engineers. We did recently hire a layout guy. We actually found him in Colorado. So when we got one guy in Maui, one in Colorado, but they're all banging on the same design and the same servers, and constantly on Zoom together. And as long as they sync up their hours, it works. Yeah. But we're looking for a couple more engineers in the short term, and then next year, as we start to scale, I'll be starting to build my team out. Kind of an army of one right now. And the plan was to bring an apps engineer on already. They'll probably be kind of, find the right guy this year and start January kind of thing. A couple of apps engineers to support a couple of our key OEMs and a couple of our key customers. And then, like I say, we'll certainly keep adding engineers. We know there's going to be a lot more software work to do as we, push the limits of what OpenMP and some of these software technologies can do. So there's some other things. Some of our partners are going to help with some of that. We're going to do some of that. So
you probably will post that information on your website, right?
Yep, we do have a job openings, in the career section of our website, and post on LinkedIn too. Yep.
Thank you.
Yeah, we do have one good layout engineer in our group. So in case you need for more, then I can ask him to talk to you.
Sure. Yeah. Bringing this other guy on has been a huge help. We've got the dry run tape out done. So the guys have done a good job, but there's still a few more things to work on. So,
yeah.
And then we just get to go do it all over again at 4 nanometer. So, yeah.
Yes. All right. Great.
Okay.
So is there more question from the audience? Please open up unmute yourself and ask.
Yeah, I'd say competition. The other kind of fun thing of competition, being in a group like RISC-V International, we have these monthly HPC meetings, and there's typically about 30 people on these things, right? And you can kind of see everybody knows. Okay, he's at Esperanto, he's at Revos, he's at Tens Torrent, right? And different things. So we all kind of know each other. It's a pretty small industry, but again, nobody's really doing exactly what we're doing yet. So, yeah. We know they're coming though.
Yeah. But in the HPC arena, how many companies are in doing HPC type of chip or system?
Well, I mean, everybody sells, has, Dell, HP, everybody, they have massive HPC teams, right? And there's a lot of HPC,
Yeah.
HPC overall, just the on-prem portion alone is like a $40 billion market a year.
Right. Yeah.
So it's a pretty good market. And all the big OEMs are there, and, NVIDIA is obviously there, and AMD and others too, right? IBM's got a shrinking portion, Power's kind of backed out of it a bit, but, it's all the kind of usual suspects, but so many of these chip companies now, and you look at the money, they're getting funded massive numbers to go after AI. If you put generative AI in your title, you're getting all this crazy money. One of my panels I led at the SCG conference back in August, one of the guys was a consultant. He made the point that it's going to be a lot like the internet bubble in his mind. There's going to be investors will completely overestimate the short-term potential of generative AI, and they will completely underestimate the long-term potential. So you look what happened with the internet, how many, dot bombs happened, but you look at us, here we are 20 years later, internet shopping, everything we do is on the internet, right? But it took a long time for it to really happen. And by the way, there was a massive consolidation in the market too when it did. So
yes.
Yeah. Okay. Let's see. Is there something in the chat? No, just thanks. Good.
Yeah.
Okay.
So it's like for every application of type oil and gas, they may have different software they need to fit into your chip.
Yep. Some are 3D FFTs, 2D FFTs, different algorithms, very much it's going to be a crawl, walk, run kind of approach with these guys. We know that. They're going to be able to recompile, 64-bit CPU code to 64-bit CPU. It's going to work. Probably going to be kind of slow, right? Then we're going to go to tune, where are the bottlenecks and find, classic and work through those. And there'll probably have to be some low-level work our guys do. There'll be some libraries that we're going to have already supplied, and they're going to be tuned. So if they're leveraging BLAST, LAPAC, FFTW, things like that, things are going to be great. But if they got a lot of their own stuff, then, we're going to have to hold their hand and get them there. And we know that. And then to eke the last 20% out, then, it's going to take, as it always does, it's kind of an exponential curve to get the most out of any system. So, but our goal is you do the software investment once and you're going to get to keep riding it. You're just going to get more cores, more cache, things like that over time.
All right. All right.
All right, guys.
I see Bob here. Do you have any announcement for your group? Bob Ascott? For this month.
We're working on our December meeting. Excuse me. I'm sorry. We have our October meeting.
Okay.
And Doug is on our board. It's a discussion on healthcare. It is on our TAGAustin.org website on the last Friday of October.
Okay.
It's there. It's all set.
Okay.
It's a great talk on topic of healthcare, home healthcare, as I believe. Special discussion.
Yeah.
Doug talked to us. What is it?
I believe the official date's October 27th for the next tag.
Yeah, I wrote that. And Doug was our speaker at our last meeting.
Yes.
We competed with you guys because we got him, and you were going to be first, but with the web issue, we got
you got to switch. Yes.
Yeah, we're all set for October. We're still the thing we're working on is the deal for the an offsite in November. I see some email that I got to go through this afternoon. So.
Yeah.
So I understand that Japan has invested a lot in the high performance computing, but they're more on the system side, but not much on chip level.
Yeah, well, they did Fugaku, right, which was an all ARM based supercomputer, and and it didn't have GPUs in it. It's one of the first ones that didn't have GPUs, and it made I think #1 in the top 500 or in the top 5 for sure. It was also on the Green 500 list, and it also turns out when you look at the peak numbers versus the more efficiency, Jack Dungara presented a great thing last year at SC on this. He had the numbers completely flip when you look at the efficiency, because he invented the Lin-Pack benchmark, right? And that's a long time ago. And we don't do dense matrix problems much anymore like we used to. Most of the problems we solve nowadays in HPC are sparse matrix. Certainly AI is. And when it comes to sparse matrix, there just aren't any good benchmarks for it. So everybody builds these supercomputers that are way overloaded, for a peak floating point number that never gets realized. So when you flip the numbers around and said, here's the efficiency of this for some real world codes, the top 3 on the top 500 were all 1%, 2% efficiency. And he said, we're spending how many hundreds of millions of dollars to get a 1%, 2% efficient machine for what we do. So there's some new benchmarks that one of his colleagues, and he's working with them at Oak Ridge National Lab to bring out, like, I think it's HPCG or something like that, which we'll be running when we have full chips. It's a full chip, benchmark suite, that are much more real world, sparse matrix, graph analytics kind of things. And it turns out Fugaku actually did really well on the efficiency scale for that benchmark out of Japan. But they didn't design the chip, it was in conjunction with ARM, they licensed that IP and worked with ARM to get that down. The Chinese, by the way, are the ones really driving hard. I kind of mentioned it with Alibaba and Tencent and some of those. They're our embargo and all this is helping drive them to it as well. But they're doing massive investments in RISC-V for data center for their equivalent of Google, right? So their marketplaces. Yeah.
Mm-hmm. All right.
All right.
So, well, any other questions from the audience? If not, then we'll thank you, Doug, for a great topic and great, information about
Thank
this
you.
new area. And congratulations for your new chip and
Thank
new
you very
market.
much. Thank you. My pleasure to be here. I appreciate it. I will get you guys the slides.
All right,
Thank
great.
you very
Okay.
much.
Okay. Thank you. Oh, one more question? Okay.
Yep. Go.
Okay. All right.
All right. All right.
Louis, you have anything to say, Louis?
No, I just say thank you very much.
Okay. Okay. Go ahead.
Thank you.
Okay. All right. Thank you.
Thank you all. Take care.
Thank you. Have a
Okay,
good
bye.
evening.
Yeah.
Yep.
Have a good evening. Okay.